All right, our next section introduces us to parametric equations. Parametric equations are sort of a different representation. We're normally used to representing a function f as a function of x with some sort of formula over here for x. But the parametric equation introduces the x-coordinate and the y-coordinate rather than having like x as a function of y determining your x1. We're relating x and y together. Like you'll have an x of t and a y of t. So you've got the idea is you've got some sort of formula, something that defines your x coordinate. Your x coordinate is changing, and your y coordinate is changing. Um, and you've got some sort of relationship between those. So you're looking at well, we'll get into graphing in a little bit, but it's a thing where you've got your rather than defining relating y and x on our regular thing where you've got you pick an x value and it determines what your y value is, and you get some sort of graph that relates those things. We have some other sort of hidden third variable that tells you the x coordinate and the y coordinate, and based on those you get a graph. So it's a little bit different way of thinking. A lot of times it's nice to think of the parameter as a time sort of thing. So you've got both your x coordinate and your y coordinate, but you've got this third sort of idea of what time that are you at there. So you're traveling down this path, but you're only there at certain times. One of the things we typically have to do is convert from parametric to Cartesian coordinates. Sometimes that's kind of a nice way to do that, to get a feel for what the underlying graph is. And what we do is you just solve for t in one of the two equations. It can be either x or y. Most of the time we want to solve for x equation because we're typically looking for y of x. But if you want things in terms of x. So I'm going to take that first equation. I've got x equals 2t minus 5. So we'll add 5 to both sides of the equation. X plus 5 equals 2t. And then divide by 2 or multiply by a half to get a version for t. And then we take that and then substitute that in for y into t for the y sort of thing. So when I substitute that in there, y of x would be 3 times 1/2 x plus 5/2 all squared minus 4 would be our equation that we're looking at, our Cartesian equation. We can multiply that out. We can simplify that a little bit if we had to, but in general, that's our Cartesian equation. That's typically the way we do it. The one thing we do when you've got sines and cosines, a lot of times it's much better to work with the trig identity. That basic sine squared theta plus cosine squared theta equals 1. Take that trig identity and use that. So what I'm going to do is I'm going to solve for sine is going to equal x over 3. And of course, cosine of t is just equal to y. And so I'm going to substitute those in there. So I'll have sine squared. I got sine is equal to uh, 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 x over 3. So I'm going to have x over 3 squared plus cosine would be y squared equals 1. And it's very useful when you've got things that are not sort of a normal relationship in there, something like this. So x squared over 9 plus y squared equals 1. Or you can multiply through by 9 if you don't like the fractions and get x squared plus 9y squared equals 9. So usually you try to solve for one variable and substitute in the other one. When you have both a sine and a cosine in there, mixed in there, working with the trig identity, sine squared plus cosine squared equals 1, generally gets you into a nicer looking form. I mean, you can solve for t, but then you've got that inverse sine, cosine of the inverse sine, and it gets kind of weird in there. It's much easier to use that Pythagorean identity. If we need to graph the parametric equation, you can always do it just by picking values for t and find the corresponding x and y values. So if like t is equal to -1, x would be 2 times -1 minus 5, which would be a -7. If t is equal to 0, x is equal to -5. If t is equal to 1, x would be 2 minus 5, -3. If x is equal to 2, or if t is equal to 2, x would equal -1. Y, and then t equals 3. You find the x values, +1 there, and find the y values. So if t is equal to -1, -1 squared is +1, times 3 is +3, minus 4 gives us 1. And t is equal to 0, I'm going to get -4. When t is equal to +1, it's going to be 3 minus 4. It's going to be back to -1. When t is equal to 2, I'm looking at 3 times 4, that would be 12. 12 minus 4, 3 times 2 squared minus 4 is going to be 12 minus 4. That's going to give us 8. So y would equal 8. And then when x is equal to 3, 3 times 3 squared minus 4 would be 27 minus 4, which is 23. And then, so then what we do is we'd typically plot these points. We'd plot the x's and your y's values. So -7, -7, and I've got a y value of -1. And I've got -5, -1, -2, -3, -4, -5. I've got a y value of -4. So -5, -4 puts us right about there. And this is what we're at when our t equals -1. Here's where we're at when t is equal to 0. When t is equal to 1, we are back here at -3, 1. When t is equal to 2, x is -1, y is 8. And at +1, I'm going to go all the way up here at 23. So I'm getting some sort of curve that's looking like something like this. I am not connecting points very well in there. But if you connect the points with a nice smooth curve here, we'll get a graph of what that is. So we have a parameter graph. I'm not doing a very good job. Well, we get the idea. What we're seeing here actually is a parabola, and this is the first equation that we looked at, and of course that is the equation y equals 3 times the 1/2 x plus 5/2 squared minus 4 is in fact going to be a parabola. And a lot of times, another thing we'll do with parametric curves is we'll add direction arrows to say what happens. So you travel along this path with parametric equations, and as t increases, you move from point to point. And it is that exact same Cartesian coordinate system, that parabola that we graphed there, but you follow it. You've got like kind of a new dimension to it. You've got a way to think about it in terms of its time. If you want to do it on your calculator, if you've got a TI calculator, it will also graph things in parametric mode. It's here under the mode settings. We have our function down here. You've got function, and then you've got parametric. So let's switch to parametric mode. And then when you go up to the y equals, you'll see an x of t and a y of t. And so if I do that same equation, which was x equals 2t minus 5. I'm going to put that in there. 2 t, and the x button here that gives you x is now typing t's for us instead. 2t minus 5 was our x value, and the y value was 3t squared, and then I think it was minus 1. Was that right? 3t squared, minus 4. 3t squared minus 4. So we can change that to change our mode with the mode setting button over here on the left. and then enter in our equations in there. And the graph will show you the graph. If you go into the window settings, you can play around with those a little bit. Our default that it set up was from 0 to 2 pi, it looks like. 6.28 is about 2 pi, and then you've got some sort of step in there. So we were graphing, we started at -2, I think, is what we started, and we went to, I think I went to 3 there. And then your t-step is going to be how much you want to change your t values in there. If I do 0.1, I'll evaluate at -2, and then -1.9, and then -1.99. And then you've got your X and Y scale as normal. X min is the left side of the graph, X max is the right side of the graph. X scale tells you where your X ticks marks are, and the Y scale is the Y min is the bottom, Y max is the top. And so here is our table there. And as you trace it, you can trace along there, and it will show you the points as you go, what your X coordinate and your Y coordinate is. You do want to use kind of a small t-step. If you use too big of a t-step, your graph won't look quite so smooth in there. It'll get kind of jagged in there as you play around with that. Oh, and another format to use, sometimes it's kind of nice, is to go over here and change your settings. I think the enter key, it's going to give me an option down here. To do this line with the circle at the front of it, that's kind of fun to do that. Oops, okay. Whoops, let me go down here. Okay, enter. And then as you graph it, it will sort of trace out as you watch. Do you see the little circle showing you where you are as it traces out your curve? So it shows your position basically with different values in there. Uh, Kind of happens kind of quick because I had a small t value. If I want to do it, if I make my t step, you got to be kind of careful. If your t step is too small, uh, it'll graph really, really, really slow. That one's not so bad. It's doing a lot of calculations to do this. If you make your t-stop really small, it'll go real small. But you can see the graph as it goes across there, as it traces out that curve in there. Desmos does do graphs as well. You can do, if you're doing Desmos as your graphing calculator, you can do parametric equations. You just put them in with a parenthesis, like your first thing. We were doing 2t plus 5, no, minus 5, I think, comma 3t squared minus 4, I believe what it was. And then it gives you, it's got a default down here. It's going from t equals 0 to 2. So you can go in here and you can change that. If I go from -2 to 3 or something like that, it shows us our graph in there. And it shows us that section of the curve that we're looking for. So parametric equations is just a new way of describing space curves, curves in space in there, but it's adding in a new dimension, a t, a third variable, a parameter, we like to call it, is that third variable. And it's nice to think about it as your position as a function of time in there. So you're traveling around this thing at a particular point. You're traveling at the curve at a particular point in space. All right.